Hi, this is Karthikeya Bansal from Bennett University, and today I am going to explain you about CFL, that is context-free language, and the closure properties related to it. So without a further ado, let's get into it. First, a bit of introduction about CFL. CFL or context-free language is a language generated by some context-free grammar. Context-free grammar are simply called as type 2 grammars also. And the major property of CFL is that it gets accepted by an push-down automata. Here, we are again and again coming through the point context-free grammar. So what actually a context-free grammar is? Context-free grammar is a set of recursive rules used to generate patterns of a string. A context-free grammar can describe all regular languages. The context-free grammar can be represented using four tuples, namely V, sigma, R, and S, where V represents a finite set called as non-terminal characters or variables. Sigma represents a set of terminals but which are disjoint from V. R represents a finite relation from V and a union between V and sigma. And S represents the start variable or start symbol, which is used to represent the whole sentence of a program. Since here we are discussing closure property, so a basic intro of closure property is also required. Closure property means that a set is closed for some mathematical operation, which means that on performing the operation on the elements of set, the resultant elements also belong to the initial set. An example of the same could be an operation of addition performed under the set of real numbers, which means if we perform addition over two real numbers, the resultant will always be a real number. Hence, we say that the real number set is closed under the operation of addition. Now, we have a basic knowledge of both what CFL is and what closure properties are. Thus, let's get into the closure properties of CFL. CFL represents many closure properties. Some of them include union, concatenation, clean closure, reversal, homomorphism, inverse homomorphism, intersection, complement, subset, superset, etc. But here we are going to discuss the top 5 of them. Our language is closed within the three properties, namely the union, concatenation, and clean closure. The properties under which our language is not closed and the ones which we are going to discuss are intersection and complementation. Further, we will explore each of them and know why are they closed or not closed. First, we have union. Let L1 and L2 be two context-free languages. Then, the union of L1 and L2 will also be context-free. To prove our statement, we have some examples. Consider L be a set of 1 and 2, which clearly represents a CFL. Now, if we substitute L1 for 1 and L2 for 2 in L, then the resulting substitutions, that is the union of L1 and L2, would represent L. Here we see L1 and L2 both belong to CFL, and the resultant, which already we have taken as our consideration, L, is a context-free language in itself. Another example could be, let's assume two languages. First, L1 representing a to the power n, b to the power n, and c to the power n, with m and n always greater than or equal to 0. And L2 representing a to the power n, b to the power m, c to the power m, with n and m always greater than or equal to 0. L3, which represents the union of L2 and L1, could be represented as a to the power n, b to the power n, c to the power m, union a to the power n, b to the power m, c to the power m, with n and m both greater than or equal to 0. Here, L1 says that A should be equal to the number of B's, and L2 says B should be equal to the number of C. The union of both represents that both the conditions should be true. Hence, L3 can be represented as a to the power n, b to the power n, c to the power n with n greater than or equal to 0, which represents a context-free language. Therefore, we can say that CFL is closed under union. The next property is concatenation. If L1 and L2 are context-free languages, then their concatenation L1.L2 will also be context-free. Here, let L1 be represented by G1 with 4 tuple of V1, sigma, P1 and S1, and L2 be represented by G2 with 4 tuple of V2, sigma, P2 and S2. Then on concatenation, the accepted PDA would represented as V sigma P and S, with V representing the union between V1, V2 and S, and P representing a union between P1, P2, S such that S1, S2. Let's take an example. Let L1 be a to the power n, b to the power n with n greater than or equal to 0. L2 be c to the power m, d to the power m with m greater than or equal to 0. The resultant concatenation would be L3, which is represented as a to the power n, b to the power n, c to the power n, d to the power m with n and m both greater than or equal to 0. This will be context free because L1 states that number of A's and B's should be equal. L2 states that the number of C's and D's should be equal. The concatenation says that the number of A's and the number of B's should be equal, then the number of C's and the number of D's should be equal. Hence, we can build an push down automata with push A, pop B, push C, pop D, giving us a condition which is context free. The last property as per the scope of our video following the closure property is clean closure, or popularly known as star operation. What is clean closure? If V star represents clean closure, then it can be defined as the smallest superset of V that contains the empty string epsilon and is closed under the string concatenation operation. Let L1 represents a CFL accepted by a CFG G1 represented as V1, sigma, P1 and S1. Then the L1 star will be accepted by the CFG G represented by V, sigma, P and S, where V would be V1 union S and P would be P1 union S, where S is a CFG represented by S tends to S1S or epsilon. For example, L1 represents A to the power n, B to the power n, where n is greater than or equal to 0. Then L1 star, that is L1 clean closure, will be a context-free language. We can say this directly because we just saw that how it is closed under concatenation. Now, let's see some of the properties which are not closed under CFL. The first one is intersection. Let L1 and L2 be two context-free languages. Then L1 intersection L2 need not necessarily be context-free. An example to support our argument would be, let's say we have two languages. L1 represented as a to the power n, b to the power n, c to the power m with mn and greater than or equal to 0. And L2b a to the power m, b to the power m, c to the power m with n and m greater than or equal to 0. An intersection between the both would be the elements present in the both. Let's represent it by a to the power n, b to the power n and c to the power n, where n is greater than or equal to 0, and this need not to be context free. Because here L1 states a and b should be equal, L2 states number of b and c should be equal. For intersection, we need to check both the conditions. That's what intersection is, proving both the conditions to be true. But since we know push-down automata has the capability to check only one such condition, hence we can safely say that the expression is not context-free. Concluding, CFL is not closed under intersection. The last property covered here is complementation. Complementation is also not closed under CFL. Complementation of a context-free language represented as L1 bar need not to be context-free. For example, let's say there is L1 with a to the power n, b to the power n, c to the power m, and both and m greater than or equal to 0. Similarly, L2 a to the power m, b to the power m, c to the power m with n and m greater than or equal to 0. If we represent the complement of L1 and L2 and their union complemented all over, then by De Morgan's law we can easily state that this expression is equal to L1 intersection L2. By multiple times using complementation, we have achieved the result of intersection. But we saw that how intersection is not closed. The two being interconvertible, it is safe to say that unlike our intersection, complementation is also not closed under CFL. Here we saw the 5 properties of CFL and how they are closed and not closed with examples. There are many more properties like cycle operations, init, prefix operations, infinite union, intersection, and many more. But they are a bit beyond the scope of this video. Thanks for now and thank you for watching.